Today's topic is quantum mechanics. So here we are. This is the beautiful face of whatever kind of creature this is. And the way that we can make these kinds of images, how that we know that we can do this, or the technology, is quantum mechanics. I'll even make it bigger for everyone's wish fulfillment. All right, there we go. So this is a consequence of quantum mechanics, is the ability to make these electron microscope images. And that is because electrons are quantum particles. Quantum particles have wave-like properties, and because they have wave-like properties, you can use them the same way that you would use photons that also have wave-like properties. Question. Don't know if this is the right time for a question, but is there ongoing foreseeable experimental work that can distinguish between various quantum mechanic interpretations? So there are a variety of quantum mechanics interpretations. There's always people that are poking at, like, what are the consequences of this interpretation of quantum mechanics, but to my knowledge, there isn't anything that is forthcoming in terms of this is definitely going to be able to distinguish between the various interpretations of quantum mechanics. So as far as I can tell, for the time being, all the interpretations of quantum mechanics are give equal predictions. They don't give they give different metaphysical predictions, like what's actually happening here. Are there new universes spawning every moment of every day, or are there are the interpretations? So right now, as far as I can tell, all of the interpretations of quantum mechanics give the same predictions. They don't have the same implications for how the universe works, but they do give the same predictions for how laboratory experiments work. Let's see. Yeah, the Copenhagen interpretation is the canonical interpretation, even if it's wrong. And there are a lot of people who have thought about this for a long time who think that it's wrong, but that's still the primary interpretation that people use, is the Copenhagen interpretation. Okay, so quantum mechanics, here we go. The quantization of energy. This was a realization that took place in the mind of Max Planck. So Planck was trying to resolve issues in optical physics, like electromagnetism. And in particular, let me scoot this down slightly. There we go. In particular, there was an observation of bright, kind of hot thermal sources, that they had a particular spectrum. So the spectrum from these thermal sources looked like this. Okay, so it has this tail over here that squiggles like 1 over lambda to the 4th, where this is lambda in this direction, and this is the intensity or the brightness in this direction. And then there was this thing that was going on here in terms of how this ramped up. So there were two different theories for what's happening. There was an explanation for why this behavior should exist. There was an explanation for why this behavior should exist. The problem was that these are both, they're incompatible both with each other and with the fact that, for example, so this curve has, the shape of this curve is a single parameter. It's a single parameter family of functions. The parameter that you have available to twist or to manipulate is the temperature. So if you have a lower temperature curve, it would come over like this. If you have a higher temperature curve, it would go up higher like that. So this family of curves only depends upon the temperature. What had been going on before is the people understood, this tail, and they understood how it behaved with temperature. But what this tail, this theory predicted, is that you would have, at any temperature, you would have this thing run off to infinity for short wavelengths. It's called the ultraviolet catastrophe. So you have some source, it has some temperature. If you only use this theory here, then the amount of radiation you get at low wavelengths or high frequencies blows up to infinity. So basically, you open up an oven, you're going to bake some cookies, you turn on the burner, the oven heats up, you open it up, and you're blasted with an infinite amount of ultraviolet and X-ray radiation, and you're immediately vaporized if you use this original formulation for what the spectrum is. So scientists knew that something else was going on with light that would force this thing to turn over. Otherwise, we would all be dead just by the fact of walking outside. We open up our door, and outside of our door, we find that there are that there is a temperature outside that is non-zero, and as a consequence, we open up the door and we're blasted by an infinite amount of radiation. Basically, all this radiation right here. So we knew that that was not correct, but we didn't know how this turned over. We didn't have a theory that would tell us how this curve should turn over and eventually go to zero. So that was what Max Planck set out to resolve, is what is the shape of the black-body spectrum. So we could measure the spectrum. We could measure the spectrum. We could explain the tails of the spectrum, but we couldn't explain how it turned over and why. So Max Planck, he sets out with it, and he says to himself, all right, self, we need to come up with a way to describe what's going on with this. And so he said, well, I can't think of... He basically had this idea that maybe you have this box, and maybe the wavelengths will fit inside this box, and wavelengths of different light will fit inside, and you get a different number of each of the wavelengths. But in order for this to work, I need to add some fudge factor in there. The fudge factor he added was H. He said, this is probably not a real thing, but it will help me do the math. So he used this fudge factor, H. He said the energy of light is proportional to the frequency. So the energy of each of these photons is proportional to the frequency, and the proportionality constant is this H quantity here. So then he starts adding up the photons, counting them, and he's able to derive a curve. That curve looks like this, and it happens to match the blackbody spectrum, the spectrum that you see from a thermal source. And when he was done, he thought that this H would drop out, and in fact, it did not. And he's like, well, I don't know what to do. Now, this curve matches what we see. It agrees with the previous theory, both previous theories. It turns over at the right spot, has the right shape. This is what we see, and this H is still around. So maybe this is some new fundamental constant. And so there you go. A new fundamental constant was pulled out of the mathematical mind of Max Planck simply because he needed some way to get the theory of radiation, like the theory of electromagnetic radiation, to match the observations that we had for black-body radiation. So that is the origin of this. Now this equation here is important, very important. E equals HF. So this says the HF is this tells you the energy of a particle of light. And what this does, and this is one of the major breakthroughs, is that it takes a wave of light. So here's a wave of light moving in some direction. It's got some intensity. That intensity is the amount of energy per square meter per steradian. So it's got some amount of energy that's flowing along with it. That energy is given by the Poynting vector, like the rate that energy is being transferred is given by the Poynting vector, which was B cross E or something like this, and there's a mu in here, maybe a C. Anyway, so the Poynting vector tells you which direction the energy is flowing and the rate that it's flowing. Okay, what this says is that the minimum size, like the minimum amount of radiation that you can have at a given frequency, is given by this quantity. So instead of having a continuous wave where you can say, I want exactly 5.2631498213112, exactly this many joules of energy from this beam of light that's coming towards me, Max Planck says you might not be able to do that. You can only count up the amount of energy that you have in discrete packets. And so you could say, here's a wavelength of light, and here's how many photons I would need to get close to this amount, but I cannot get exactly that amount unless it happens to be an integer multiple of Planck's constant. So Planck's constant times the frequency of light that I'm considering. So if I'm considering light at twice the frequency, then the minimum photon energy is going to be given by this quantity. So this equation, it's a little bit weird, and it's a little bit counterintuitive or like not obvious that, okay, this equation, therefore quantum mechanics, right? Here's an equation, quantum mechanics, there we go. Problem solved. No, it's this equation. This says this is the minimum amount of energy you can have in photons of a given frequency. And any beam of photons, so any ray of light that comes at a given frequency, comes in integer multiples of this amount of energy. This amount of energy given by this quantity. So light of a given frequency is going to be broken up into particles called photons. Right there. Thank you for that sub. I appreciate that. So now we have quantum mechanics. We can now quantize the electromagnetic field. It is broken up into little pieces. Now, we've seen that light has interference properties. We already know that light has interference properties. From a few discussions ago, we talked about how you can get diffraction, you can get interference, you can produce different things, different colors that bounce off of different surfaces based upon interference properties of light. That is a wave-like property. Waves interfere with each other. Like these photons, now we're saying that light is actually a particle and not a wave. And so why is it that they can interfere with each other? And more importantly, if they are actually particles that are broken up into these little packets, as Max Planck's theory kind of forces you to believe, then how come we can't measure the particles? And it turns out that we can measure the particles. Okay, we can measure the particles. And the way that we do that is the following. And this is what Einstein was able to explain. So Einstein wrote a paper to explain the photoelectric effect. And this is where we get to pull together all sorts of knowledge that we have. All right, so here is this. I have a battery down here, and I connect it up like this, and I have a gigantic capacitor plate inside of this vacuum chamber. So this is vacuum here, vacuum. I have a capacitor plate, and I've got a battery in here, and I have a bunch of electrons that are piled up on this plate. Okay, but they can't get across this gap because it's not an electrical conductor. There's a vacuum. The vacuum is a very poor electrical conductor. And so how do you liberate these electrons and allow them to jump across this gap and flow around the circle? That is the question, the big question that was posed. Well, anyways, that's the question that needs to be resolved. And so there were experiments that were done that showed that if you shine a flashlight, you take a light of a given color, and you shine it on this thing, that if you had a gigantic red flashlight, so let's say you had a red flashlight that was this big, okay, it's got like 50 batteries in it like this, you have this light bulb, it's a super bright red light bulb, and it blasts out all this red light. Okay, if you take all this red light and you shine that flashlight on this side of this detector, then it turns out that nothing happened. You had no current. Oh, I need to put in a detector. So here is my capacitor plate with all these electrons piled up on it because they're trying to flow because the battery's shoving on them, pushing them around. I have a thing here that measures electric current, and I get 0. Here is 0 when I'm using this battery. Or I could take a separate flashlight. Here's a tiny little flashlight that only uses like a single AA battery or even a AAA battery, so it's a little wimpy flashlight. But this is blue light. Blue, this one here is red. The red light caused no effect. The blue light, which has shorter wavelength or higher frequency, you shine the blue light on this, and then all of a sudden the electrons are jumping across, and the needle comes over here, and you get current. Current's measured in amps. So all of a sudden the current will start flowing because these electrons are liberated. They're liberated from their captivity on the surface of this thing, and they jump across that gap and allow the current to flow. And the only difference was the wavelength of the photon. In fact, you can bias it. You can have a really super powerful light that's in red and get no effect, and you can have a super wimpy light that's in blue and get an effect. Okay, this is evidence that rather than being a total amount of energy that's deposited on the surface here, it's that when the energy arrives, it has to arrive in big enough packets, big enough pieces of energy in order to free the electrons from the surface and have them jump over. Okay, so you have to hit it with enough energy. That implies that the energy comes in discrete bundles. And that, again, that coincides with E equals HF, the fact that light comes in packages, energy packets that are this big. And if you have a higher frequency, then that's a higher energy, and that excess energy is able to liberate the electrons from one side and allow them to jump across the other side. So red light has longer wavelengths or smaller frequencies, and so has less energy per photon. Blue light has more energy per photon by about a factor of 2. Right? Red light's around 700 nanometers, blue light's around 350 nanometers. And so that jumps across here. That factor of 2 in energy could be enough, depending on the substance, to have it jump across there. Now, each substance here is going to have a different energy associated with it. The electrons in the surface of this plate here are going to depend upon whatever that material is made out of. You could have a material where the energy is where the electrons are very, very weakly bound to the surface, and therefore it's easy to knock them off. Or you could have a substance where the electrons are tightly bound to it, and it takes a lot of energy to knock it off. And that is where the function, it's called the work function. Work function. The work function is the amount of energy that it takes to dislodge the electrons. So some substances like mercantile, so that's what, Mercatel is HGCD. Is that it? Tellurium? I'm not sure what tellurium is. Maybe that's... Anyway, tellurium. It's mercury, cadmium, tellurium. Mercury, cadmium, tellurium, Mercatel. These devices have a very small work function, which means that it takes low energy photons are able to dislodge the electrons. Where if you have silicon, for example, silicon has a higher work function and it takes more photon energy, higher frequency photons, to dislodge the electrons from silicon. So let's suppose that you wanted to make a digital camera. Digital cameras work off of quantum mechanics. So if anyone's like, why do we ever study quantum mechanics? You can say, well, digital cameras, man. So digital camera. Here is a digital camera. It's got these pixels. These pixels are arranged in such fashion like this. There's a little electromagnetic field that will trap any electrons in these pixels like this. So light comes in, hits the surface of this pixel, so that we're zooming in on the pixel. Light comes in, hits the surface, and will dislodge an electron from that surface, and that electron will get trapped in this well. If you have lots of light coming in, you'll just dislodge many electrons, and so you have a whole set of electrons like this. And then when you render the image, these electrons are shifted one thing at a time over to the edge, and then shifted down to a device that counts the number of electrons that are in it. So you count the number of electrons that have been dislodged, and that tells you how bright the light was in this particular pixel. So each of these pixels is going to get its own collection of electrons. Those electrons are going to be shifted down to the device, I don't remember what it's called, the drain or something like that of the CCD chip, and counted up to tell you the number of photons that landed. So that's how a CCD camera works. If you're using silicon as the basis for your CCD camera, then it's going to have a work function. We can look this up even. It's going to be amazing. Let's take a look and see. What is the work function? Work function of silicon. The work function of silicon. Let's see if we've got a table in here maybe. Where's the silicon? Where's this table? Looked like there was a table. Here we go. All right, work function of elements. Silicon is on here. Don't see it. Not seeing. Oh, here's silicon. So work function of 4.6 to 4.85 what? Electron volts? Yes, electron volts. 4.6 to 4.85 electron volts. So the silicon probably has to be doped because 4.6 electron volts, that's the energy that it takes to dislodge an electron. 4.6 electron volts is quite a bit higher energy than than visible light. Visible light is about 2 electron volts. So there may be some temperature aspects that come into this, although I suspect not, at least not initially, because as you cool these things down, you get better noise performance. So I suspect that the silicon is actually doped slightly to reduce this work function and put so it becomes a semiconductor. So there's more electrons near the surface that are able to, there's a smaller band gap, a smaller energy that it takes to dislodge an electron from the surface. Anyways, so silicon has one work function that allows it to observe photons. If you had pure silicon, you would be able to observe photons of this energy and higher energy. Where if you look at mercury or cadmium, mercury's Hg, right? I don't see mercury. Anyways, you have lower energy things. Do I see cadmium? Here's calcium. Cadmium here, 4. Tellurium, is tellurium on here, 4.95. So anyways, these are pure substances. When you dope them up, then it puts more electrons, makes more electrons available to you that are easier to dislodge. So yeah, so it's not, I originally thought that I might be able to get away with just pointing out, oh look, you can make it out of this and it's got a lower work function and that makes your detector better. But it clearly shows that it's the alloy, it's the doped substance that matters. All right, anyway, so you have a silicon CCD, which is what you'll have in your phone camera, is sensitive to visible light. So this is able to detect particles at about 1 electron volt. However, if you're looking in the infrared light, silicon isn't capable of detecting infrared photons. Infrared photons are going to be like 0.1 electron volt, so 10 times or 1/10 the amount of energy per photon. And so the electrons are too tightly bound for regular silicon CCD devices. I suspect there's probably a voltage in there as well. At some point I'll have to look at like how CCD chips are designed. There might be a voltage that's applied that makes it also easier to dislodge these things. Anyways, the point is it takes some energy to dislodge the electrons. They get into these little pixels, and in those pixels, when you drain the CCD chip, the electrons will jump down, and then you count the number that are in there. For a silicon chip, you can detect visible light photons. So visible light energy photons can come in and dislodge the electrons. However, the infrared photons, which are about 1/10 the energy, are not able to dislodge the photons. And so you need to change the type of detector. You need to change the material that you're using to make your digital camera. So if you have an infrared digital camera, you do it out of this Mercatel, Mercatel detectors, which have a lower work function and are able to detect lower energy photons. They're harder to make, otherwise they would be the standard practice. But if this is what you need to detect, then you have to have a detector that can do it. So the James Webb Space Telescope is designed with these kinds of detectors because James Webb is specifically geared towards observing things in the infrared, not in the visible. I mean, it can still see things in the visible, but it's specifically designed to look for things in the infrared. Unlike Hubble, which was designed primarily to look at things in the visible light. So, how do thermal cameras work? Thanks for those 100 bits. How do thermal cameras work? Thermal cameras are looking specifically at infrared detectors. So they probably also, if you have an infrared digital camera, IR digital camera, it's probably one of these kinds of things. Infrared digital camera. Let's see if we can see what these are made out of. Does it give... Are there cameras that detect temperature and not voltage? So infrared cameras, they don't detect temperature either. They detect infrared light. So basically what you have with an infrared camera is you have an infrared source. Okay, so you have like a visible light source. The black body spectrum of a visible light source will look like this. It will peak in the green at about 500 nanometers. Okay, and this will be at a temperature of about 6,000 Kelvin. Okay, so the sun is around 6,000 Kelvin. And it will have a particular spectrum. It peaks in the green. That's where eyes are most sensitive as well. So the rainbow is at the top of this spectrum for the sun. For humans, our temperature is what? 300 Kelvin? A little bit more than 300 Kelvin, which is about, what, 1/20th? So this one peaks at 500 nanometers. Humans will peak at 20 times this length. So that's half a micron times 20 that's 1 micron. That's 10 microns. So humans will peak at 10 microns. Okay. A black body spectrum from something at 300 Kelvin is going to look like this. And instead of peaking at 500 nanometers, it peaks at 10,000 nanometers, or 10 microns. So when you have an infrared camera, you know, the visible part of the spectrum is here. Humans don't glow. We are brighter in the infrared than we are in the visible part of the spectrum. And so when you see an infrared camera, you're actually observing in this wavelength range, observing the infrared light that's coming off of us. And so people call infrared light heat. It's not really heat. Heat is just another name for energy, but it's infrared photons that carry energy with them. So that's how that works. Mercury cadmium telluride. Also cadmium mercury telluride, mercatel, mercat, MCMT is a chemical compound of cadmium telluride and mercury telluride in a tunable band gap spanning the shortwave infrared to the very long infrared regions. So this shows the energy gap, that's how much energy it takes to dislodge the photons. At 300 Kelvin, if you cool it down, then you get better performance. So this is like 80 Kelvin thing. And so you can see at as you change the fraction, so this is how you dope it. Okay, so you dope it with this cadmium, function of the cadmium composition. So you dope it with cadmium, and that gives you a change in the energy gap. So you say, I want to look at a specific energy range, and then you dope it with this substance in order to get the energy gap. You have to overcome that energy gap in order to liberate the electrons as they leave. Okay, so here we go. That is the photoelectric effect. That's what it's called. The photoelectric effect is the effect of photons dislodging the electrons from the surface of these different substances. So let us take a look and see if we're missing something. So that's the photoelectric effect. Photon energies in the electromagnetic spectrum we've talked about. Photon momentum. So we mentioned before that photons have momentum, and people have asked, how do you arrive at this photon momentum when the photons are particles that don't have mass? Okay, recall that momentum for classical particles is mv, and we saw in the special relativity thing that what do you do with massless particles? And what you do with massless particles is the following. You say, with massless particles, you got E squared equals P squared plus M squared. Okay? And if you convert the units into SI units, then it's the energy squared is equal to PC squared plus MC squared, right? This is E equals MC squared. At rest, when there's no momentum, this P is momentum. When there's no momentum, then this term goes to 0. And you're left with E equals mc squared when you take the square root. If you have a massless particle, on the other hand, this term goes to 0, and that gives you that energy is equal to P times the speed of light. Okay, or you get E over C is the momentum. P is E over C. Okay, well, I can, what else do we know? We also know from Planck's formula that the energy of a photon is equal to HF. So we have, this is the energy of the photon, and this, well, my Mathematica license, it faileth. We get this E equals HF, and we have this P equals E over C. I can substitute these, because it's the same photon, so they have to have the same energy. I can substitute this one in here, and I get that the momentum of a photon is HF over C, which is also equal to, if I rewrite this, hc over lambda, where lambda is the wavelength. Wait, hold on. This is the energy. That's the energy. The momentum is h over lambda. Okay, so the momentum is h over lambda. Once you get, the frequency of light is related to the speed of light, right? The speed of light is equal to the frequency times the wavelength, and so I can make that substitution here. So the momentum of a photon is h over lambda. The energy of a photon is hc over lambda. So those two things are useful. So this is the momentum of a photon. So photons, individual photons, carry momentum despite the fact that they have no mass. And this is the relationship that tells you what their momentum is. You use special relativity. Without special relativity, you can't do this. So special relativity tells you how to find the momentum of a massless particle, and quantum mechanics tells you how to get the energy of a quanta, a single photon, and then you put it in, and that's what you get. So there's that. So that's photon momentum. Now, this particle-wave duality, that is what's interesting here. So now let's come back to this recognition. We now know from the experiments of interference that light is a wave. Photons are waves. We also know from the photoelectric effect that photons are particles. And so photons are waves and they're particles at the same time. What does this mean? Well, it means a number of things. One is that there must be a wave equation that that the photons must satisfy. So there's a wave equation that the photons have to satisfy, and there are certain behaviors that these particles, or that these objects have, that make them behave like particles. And that makes you wonder, if photons can be simultaneously particles and waves, then what about electrons, for example? Electrons are known to be particles. Do electrons also satisfy a wave equation? Is there a momentum or a frequency that's associated with an electron? And the answer to that is yes. Is there a wavelength associated with an electron? And the answer is yes. And for that, we use this. So the momentum of a photon is equal to h over lambda. And so the momentum, you just can assign this by fiat to a massive particle. The momentum of an electron is also given by h over lambda, which tells you that the wavelength of an electron is h over its momentum. So electrons have a wave-like properties. What is the wavelength of an electron? The answer is this right here, h over the momentum. You increase the momentum, the wavelength gets shorter. Okay, what are we talking about? The question is, wouldn't that mean that all particles are waves as well? And the answer to that is yes, all particles are indeed waves. All particles satisfy the wave equation. Okay, so basically you take an electron, you find its momentum, you put it into this equation, that gives you the wavelength. So let's see what kind of things we're talking about here. What is the momentum of an electron? So the momentum of an electron is mv, okay? So that's the momentum of an electron is mv. The mass of an electron is, I don't know how to do this. I know the mass of an electron is 511 keV in keV per c squared. So what do I need to do? If I were to go like this, the momentum is mc squared v over c squared. I know that quantity. And so now what? That gives me 511 keV. KeV. We get that. So that's 5 times 10 to the 5. Anyways, 511 keV. That's a K. Is that part? And then how fast are these things moving? Let's just go with the mass. Okay, so back to this. Momentum is equal to. Hold on. I'm looking for the wavelength is equal to h over the momentum, which is equal to what? hc over pc. Okay, here we can do it this way. hc over pc. Pc is mv times c. And so if I multiply and divide this by c, I get mc squared v over c, like that. That's what the quantity I was looking for. Okay, and this one I know is 511 keV, which is 0.5 MeV, and v over c, let's say that it's moving a pretty small fraction of the speed of light. So let's say it's moving at, the speed of light is 3 times 10 to the 8 meters per second. And let's say that we're beaming this from a cathode ray tube or something like that, so it's going to be way less than that. So we're talking about maybe 10 to the minus 5. Okay, that's going to give us, this is 5 times 10 to the minus, or 5 times 10 to the 6. This is 5 times 10 to the 6, and v over c is going to be 10 to the minus 5. That's 5 times 10 to the, actually it's 5 times 10 to the 5, and this is going to be times 10 to the minus 5, which gives us 5 electron volts. There we go, there's the math. If I pick the numbers right, then the math is easy. And now I take this and I put it up in here for that, and I get lambda is equal to hc, which is 1240 eV nanometers, and I've got divided by 5 eV. And so these slow-moving electrons, I can divide 1,000 by 5. 1,000 divided by 5 is like 200 nanometers. So slow-moving electrons are going to have wavelengths of well into the ultraviolet. The wavelengths of these electrons are well into the ultraviolet. If I speed it up, if they're moving faster, then this wavelength gets even shorter. And so the typical wavelength for electrons, 5 eV is small. That's 5 volts. That's taking an electron and accelerating it across 5 volts. If you increase the speed of these electrons, then this wavelength gets a lot smaller. And so you get smaller and smaller and smaller wavelengths. Okay, how does this relate to, why is it that electrons are able to measure small details? The answer is, okay, so you accelerate them across more than 5 volts. Let's say that you have an electron microscope where you're accelerating the electron across 5,000 volts. Okay, so now instead of 5 electron volts, you have 5,000 electron volts for the energy of your electron, and that is 1/1000th of this thing. That's 0.2 nanometers. The wavelength is 0.2 nanometers. If you go to 50,000 volts, then you got 0.02 nanometers. That's a much smaller length. This is a tiny wavelength. Visible light is 1,000 times longer than this. Okay, so at 0.2 nanometers, now you're using 0.2 nanometer wavelengths to measure things, And whenever you're taking a picture of something, suppose you want to take a picture of some feature. So here's a bump on something, a bump on a log, and you want to take a picture of this feature. You won't be able to measure the properties of this feature if the wavelength of light is gigantic. With a gigantic wavelength light, it's not even going to see this. It's just going to bounce off of it. It's going to see this whole surface instead of that little feature. If you want to measure the properties, like the size and shape of all these different corners and stuff like that, you have to have a wavelength of light that is short compared to the feature that you're measuring. So if you have electrons, that you can now accelerate them to some speed and shorten their wavelength down to like 0.1 nanometers, then you're able to measure features on the surface of some object that are on the scale of 0.1 nanometers. Okay, and that is what is seen here in this image. So the reason we get such fantastic images using electron microscopes is because the electrons have a short wavelength. This forces electrons, so electrons have to have wave-like properties. Electrons have wave-like properties, and a consequence of that is that we can make these kinds of images. If electrons only behave like particles, we would not be able to have these kinds of images because they wouldn't have a wavelength associated with them, and we wouldn't be able to resolve this. Is there a probability of a larger wave seeing a smaller feature? So what happens if the wavelengths are longer is that the scattering surface changes. So if you have a sphere like this, if you have really short wavelength light bouncing off of it, then the cross-sectional area of this is pi r squared. So short wavelength light comes in, bounces off a sphere. The surface area, or the cross-sectional area that you see here, is pi r squared. If you have long wavelength light that comes in, what happens is the light wraps all the way around the feature and interferes with itself, basically. So the light wraps all the way around, and the scattering cross-section, the cross-sectional area for long wavelength light is actually 4 pi r squared. That's weird. That's the whole surface area. So the cross-sectional area for long wavelength light is the entire surface area of a sphere. And then as the wavelength gets shorter and shorter, then you get to this pi r squared. And so what happens if you have really long wavelength light is that you have, let's see if I can find a picture of interference. Interference around a, let me go long wavelength scattering. Long wavelength scattering. Let's see if there's an image that shows that. No, not really. But this is what I'm talking about here. That blue light, so short wavelength light will come in and it will interact with stuff and scatter in all directions. Long wavelength light will come in and basically pass by. So I don't see the image that I was looking for here, so I will just have to draw the image that I was looking for. So buckle in, here we go. So if you have a scattering center, like some object that you're scattering around, the short wavelength light will bounce off and reflect off the surface. The long wavelength light will come along and you'll get diffraction off of the two ends. We've already talked about diffraction, that you have a source that's here. The diffraction pattern will develop on the other side, and you end up with like a wavefront that looks like this. So you get this cone that expands that has a deviation in the electromagnetic field. So this scattering center will cause a deviation in the electromagnetic field. That deviation in the electromagnetic field will produce an interference pattern or a diffraction pattern on the tail side, like on the back side, the downstream side of this scattering center. Over here, you'll see basically no effect. Over here, you'll see basically no effect. As the wavelength gets longer, the region behind it gets bigger. And so it starts to spread out more. Is that right? As the wavelength gets longer, this interference pattern will, like the shadow of the interference pattern will grow, I think is what happens. So let me see if I can find like quantum mechanical scattering. Here we go. This is what I'm talking about. That's what I'm talking about right here. Okay, so you can see the stuff coming in. The classical regime is these billiard balls. The quantum regime is these wavelengths. So here's these wavefronts that come in, and then you get this diffraction pattern that shows up behind it. So the width of this diffraction pattern is going to depend upon the wavelength of light that impinges upon that surface. I believe what's going to happen is that with short wavelength light, you basically get an abrupt edge, and with long wavelength light, you get a larger scattering pattern because it's scattering off the entire surface. So there we go. is that thing the shadow in the middle of every sphere from Veritasium. I believe that what's happening there is you get the light can actually combine behind you and get a bright spot over here. So the light comes in, kind of works its way around, and then you can get a bright spot behind a sphere from that. I think that's what it's talking about in that particular video. Okay, let's see what we got. Wave particle duality. Okay, so now we know that matter also has waves, or also behaves like waves. And so you can send particles through wave-like detectors that detect waves, so like a double slit interference apparatus or something like that. You can send these particles through those apparatus, and as long as the sizes of the things are correct, as long as you have the size of the slits be appropriate for the wavelength of the electrons that you're sending through, then you should get the same interference pattern. And the weird thing is that you're sending individual particles one at a time through that interference pattern, or through that apparatus, and the particle is interfering with itself. So if we look at electron interference, okay, here is electron interference. It's got this is a very, very famous image that is in almost every introductory textbook. Okay, so you're sending single particles at a time, single electrons through a double slit experiment. So here are your two slits. We have one slit there, one slit here. They have to be small because the electrons have small wavelengths. Here's your beam of electrons coming this way. The electrons are going to go through both slits. Each electron is going to go through both slits, but because it's a single particle, it's going to land at a single spot on your detector. So here's your detector over there. So there's where your particle lands. You have another particle land over here, other particles, and as you look at where these particles build up over time, one particle at a time, you can send in one particle at a time, and it will start to populate a pattern. And you can see from that image that I just left, you can see that it populates and produces these fringes, this interference pattern. That interference pattern comes because that means each individual electron goes through both slits. You send one electron in, that electron goes through both slits. As it comes out of both slits, it interferes with itself and produces excess probability of the electrons being detected in some regions and not in others. Okay, how does it go through both slits? Well, the electron turns out to be not an isolated localized particle, but it's actually a wave function that describes the probability of the electron being at any given point in space and in time. So it's usually given by the letter psi. So that is the electron wave function. It has an infinite extent. Even though the probability goes very small, basically goes as like a Gaussian, for example. It's going to fall off quickly as you get away from the beam of electrons you have here, but it doesn't go all the way to zero. And so you have this extended electron wave function that's going through both slits. And so a portion of that probability is going to go through here, a portion of that probability is going to go through here, and then the wave the wave function as it emanates from here and from here will interfere with itself to produce the interference pattern that's on the other side. Now, we talked about this, I think it was last time, it may have been 2 times ago, what's actually going on here. And the answer is that the single wave function goes through the whole apparatus, interferes with itself, and produces this. If you put a detector here, for example, that detector, as the wave function comes through, the electron wave function comes through the hole, if the detector gets fired, so what's actually happening as this wave function comes through the hole is that you get a wave function that looks more like this. And then these two sources will interfere with each other. So a single wave function comes in, this kind of bimodal wave function comes out through the holes. That's the 2 point sources that it's going to emanate from. And then those 2 point sources are going to interact with each other and produce the interference pattern. So when the wave function is on the outside over here, it's got this bimodal shape. Then if you have a detector here, it will detect the wave function, which means it will detect either that the electron came out of this one or it came out of that one. It will collapse the wave function down to where the detector is located. So here's your detector. You now made the measurement, and so the wave function has collapsed. Here is your single electron, and so that single electron is going to come over here and it's going to pile up on the thing. So if you have a detector that detects the electron near the slits, you'll get 2 bright spots. You get bright spots that go from the detector, from the electrons that pass here and are picked up by this detector. That will produce this bright spot. And the electrons that are not picked up by that detector are then must be in this part of the wave function and then are going to produce this bright spot. If you remove that detector, then you've removed this collapse of the wave function, and the wave function will interfere with itself and produce the interference pattern. How does it detect? Yeah, it detects by either looking at the Coulomb field as it comes through. You're going to have an electron come by. It's going to create a magnetic field because you have basically, as the electron moves by, it's going to have a magnetic field that spirals around it because that's what electrons do. You have a moving charge. And so it's going to be something like that that produces it. Okay, so that is what's going on there with the wave-particle duality. Electrons behave like waves. It has a wave function. That wave function satisfies the wave equation, and so all of the wave-like properties are going to be adhered to as well. Now, what's really going on fundamentally is a bit more deep than this, and that's what we're here for, is to learn about like what are the deep aspects of this. What's really going on is you have a wave function here, and it is going to advance through space. As it does, it has its phase. The phase of this wave function is going to be given by e to the I s over h bar, something like this. I think a to the I s over h bar, where s is the action. Action. That's a c. Okay. This s up here is the action. The action is the Lagrangian. So the action is equal to the path integral across some path of the Lagrangian times what, dt? Is that what it is? Energy times, I think that's what it is. Yeah, Lagrangian times dt. So you integrate over time some path. Here's the path that you're integrating. The particle is going to follow this trajectory. You integrate along that path over time, your initial time, final time, and you integrate the Lagrangian. The Lagrangian itself is the difference between the potential energy. I think it's kinetic energy minus potential energy. So the Lagrangian is equal to the kinetic energy minus the potential energy that this object has. So you have some electromagnetic field. It has some mass. It's got a whole bunch of other things that are going on. Maybe it interacts with gravity. That all contributes to the potential energy, and then you have the kinetic energy, and you integrate that path along the Lagrangian. Okay. When you're done, that's going to leave you with some value for the action. The action has some value. That value is going to come up here, and it's going to tell you the phase of your quantum wave function. An important thing to remember is that an expression that looks like this, the exponentiation of a complex number, you take this thing, you have a complex number, you exponentiate it, that is going to give you e to the I theta is equal to cosine theta plus I sine theta. Okay, so now you have, the complex phase, that's the thing up here, the phase of this wave function, this theta, theta is going to be equal to the action divided by h bar, by Planck's constant. And so let's take a look at that. So that means, let's just take a look at this cosine part. That's going to be cosine, the phase of my wave function is going to be cosine of the action over h bar. So as the action grows in value, it will cycle through 2 pi relative to h bar. So if the action ends up being 2 pi times h bar, then the h bar cancels and I get 2 pi, and I'm back to the phase where I started from. If the action is 3 pi, then I get 3 pi times h bar, then I've gone 1.5 times around. If the action is 6,243,001.856, something, then I divide that by h bar, and that tells me how many times I've wrapped around, that over 2 pi, how many times I've wrapped around this phase. Okay, so this phase is going to advance along with the action. So what happens in real life is that here is your particle to start with, here is your particle to end with. So I emitted it from some source here, I detected it at some detector here, and the particle is actually going to take all paths, all possible paths, even a bowling ball. So I think we did this once before. You have a bowling ball, it's going to take all possible paths to get from one place to another. All of these things are equally likely. Each path is equally likely. And so you then add the e to the I path 1 plus e to the I path 2 plus e to the I path 3. The phase of all of these things are going to add like this. Well, the phase of all these things adding, if they add out of phase with each other, then they basically cancel each other out. But if they add in phase with each other, then they will combine and give you a signal that's left over. They'll give you a non-zero signal. So what happens is that the classical trajectory of a particle whether it's a quantum particle or a classical particle, is a location where its action is minimized. So you minimize the action. So here's the action for all these different paths. I know I've drawn this picture before, but we're doing it again anyways. So here's the action for all these different paths. And the minimum action is going to be right here. So all of the paths that are near the minimum action are ones where the phase is more similar to each other. Okay, so the phase of this path that you get, so that's S1 over H bar, and the phase of this path right here is also going to be approximately equal to S1 over H bar. These two phases are going to be similar, and so they're going to add coherently. On the other hand, so that's because the slope here is negative, or I'm sorry, the slope here is 0. So there's no slope, which means that as you change paths, there's no change in the action. If you make a minuscule change in your path, minuscule change in the action, then, a minuscule change in the path in this direction is going to correspond to a minuscule change in the action, okay? Because that's where the action is minimized. On the other hand, if you're over here, a small change in your path in either direction is going to cause a fairly large, a linear change in the action. This is a quadratic change in the action, which means that small changes are going to be negligible. This is a linear change in the action, which means that any change in the path is going to be directly proportional to the change in the action. And as long as we're measuring the action in terms of a small quantity h bar, which is what, like h bar is 10 to the minus 34 or something like that. It's a tiny number. So it doesn't take much change in the action to completely scramble the phase. A small change in the action, a small deviation from the classical path is going to completely scramble the phase, and therefore things are going to add incoherently. And so the path that you take is going to be further and further constrained to be near the minimum action because all of these other possible paths are going to add incoherently. So if you have a massive object where you're looking at the action is going to be 1/2 mv squared minus what, mg or something like this. So this is the mass is going to be huge compared to h bar. Let's take a look at h bar as so that I know what it is. H bar in joules. H bar in joules, Planck's constant in joules, has a value. H bar in joules has a value of 10 to the minus 34. So I was right before. 10 to the minus 34. What does that mean? So joules, like a joule of gravitational potential energy is a kilogram lifted 10 centimeters off the ground, right? Because mg is, mgh is the energy. Oh, I missed that. There's an h here. 1/7 squared minus mgh. Okay, so if g is about 10, m is 1 kilogram, so you have 1 kilogram, 10 for g, and then h.1 gives you a joule of energy. All right, so you have a 1 kilogram small bowling ball, and you lift it 10 centimeters off the ground. You've gone 10 to the 34 times around this clock. Okay, that's the difference. 10 to the 34 times. The fact that it's 10 to the 34 plus a little bit and 10 to the 34 minus a little bit is completely irrelevant. I mean, these are totally, completely different scales. So you lift this thing 10 centimeters off the ground, you've wound the quantum mechanical phase 10 to the 34 times around. And so it scrambles, like it's completely scrambled. On the other hand, if you take an electron, if you take a look at the mass of an electron, mass of the electron is like 10 to the minus 31 kilograms, right? 10 to the minus 31 kilograms. So the mass of electron, mgh, this is 10 to the minus 31. That gives you a 10, so that's 10 to the minus 30. And then there you go up 0.1, that gives you 10 to the minus 31 again. And now you're talking on a scale, 10 to the minus 31 compared to 10 to the minus 34. Those are scales where you can actually see quantum mechanical effects. So if I have an electron and I lift it up in a gravitational field 10 centimeters, then we're talking about a 1/1000th. This phase is only spun around 1,000 times. Okay, 1,000 times is a lot easier to count than 10 to the 34 times. So what if instead we take an electron and we add a little bit of kinetic energy to it to make this difference kind of small, but maybe we move an electron up. I mean, 10 centimeters is huge compared to an electron. What if we moved it something that's atomic sized? So you take an electron, you move it in a gravitational field, an atomic distance, which would be like 10 to the minus 4 well, it's even less than that, but let's pretend for the moment. So it'd be like 10 to the minus 10. Okay, so you move it up some atomic distance, 10 to the minus 35, 10 to the minus 10 in a gravitational field, or maybe even an electromagnetic field. It might not matter that much. And now we're talking about something that is spinning around a tiny fraction of this phase. The phase is advancing a tiny fraction as you go to slightly different paths. And as a consequence, many of these paths can contribute to the behavior of the electron wave. And that's why you can have a macroscopic double slit experiment, because you're working with electrons and short distances and low energies. Then the wave function is going to be big. The action for a variety of different paths are going to differ by a small amount. And so you can get quantum mechanical behavior instead of classical behavior out of an electron. So you're changing the energy scale by going to small particles, so that in this action, which is the kinetic energy minus the potential energy, we're taking this quantity and we're dividing it by h bar. And so if this quantity is going to be comparable to h bar, then you get all the weird quantum mechanical effects. If this quantity is on a completely different scale than h bar, much bigger, like 30 decimal places bigger, then you get classical behavior. And that's how you transition from classical mechanics to quantum mechanics. So in real life, what happens when you have an object leave one location and arrive at a different location is it actually does travel. Its wave function travels through all possible trajectories to get here, even ones that go around the Earth backwards and come over this way. It goes through all possible trajectories, but the only ones that can contribute are the ones that minimize the action and produce the smallest variation in the action over that distance. And how much quantum effects, like how big the quantum effects can be, are based upon small deviations from the classical path relative to Planck's constant. So you can get quantum mechanical behavior of a bowling ball, but only on a scale that is small compared to h bar. So that's what's really going on with these quantum mechanics things. All right, what do we got? We got the probability, the Heisenberg uncertainty principle, so we'll talk about that. All right, Heisenberg uncertainty principle, last thing for today, Heisenberg uncertainty principle. The Heisenberg uncertainty principle says that you cannot measure the position x delta v, delta p, momentum, position momentum are conjugate variables. This must be less than, like your uncertainty in position, your uncertainty momentum have to be less than h bar. There's probably a factor of 2 in there, but who cares about the factor of 2? It basically says there's a size, there's a box. So the reality is that we live in a we have a 6-dimensional coordinate system that we use. It's actually 8-dimensional. We have an 8-dimensional coordinate system that we use to map things out, or like to express things. Those coordinate systems are the positions that we can have. We have 3 spatial positions, x, y, z, and time. So we have 3 spatial positions and 1 time position. And we also have different velocity states, right? The movement of the particles in these positions. We have to specify all of those coordinates. So that's going to be the momentum in the x direction, the momentum in the y direction, the momentum in the z direction, and the momentum in the time direction, which is the energy. So there's actually an 8-dimensional space. And you can describe the motion of a particle in momentum space. So you can say, I have a wave, for example. Here's a wave. It's got a wavelength, and it's moving in this direction. You can specify this wave by simply putting it in what is the momentum of the wave. So the momentum of a plane wave is going to be a delta function with a specific momentum that corresponds to this wavelength, right? P is c over lambda. I'll get to that question, amateur wizard. I'll get to that question in a moment. So if you have a pure sine wave, then it's going to have a fixed momentum. If you have a sine wave that's not quite pure, let's say you have a sine wave that kind of moves like this, it's almost exactly a perfect wave, but it does kind of spread out in the sides. This will have not a perfect momentum. It actually can have a range of momenta that can contribute to it. So you might have, in momentum space for these photons, you'll get something that looks like this. So that's the dominant wavelength. That's like the wavelength you'd call it. But then you get some light that has a wavelength on either side. And that is going to cause the wave, kind of like if you have 2 windshield wipers that are slightly out of phase with each other, moving at slightly different frequencies. So it might start off like this. You have these 2 different window wipers, but if one is moving at a slightly different rate, then eventually they'll be going in opposite directions, and then eventually they'll catch up with each other and go back in the same direction, and then eventually they'll get out of phase again and they'll be going in opposite directions. So that is what's going on with these kinds of things. And the beat frequency, how long they stay coherent with each other, that's the beat frequency. That's also would give you, for example, the coherence length of a laser. So if you have a laser has a prominent or a single spectral line. They don't always have a single spectral line. You can laser at specific laser frequencies. There can be a spread in those laser frequencies. A laser that has a broad laser line will have a shorter coherence length. So the wavelengths will be, if you go many centimeters away, they're typically measured in centimeters. If you go like a meter away or 2 meters away, it's no longer in phase with each other. You'll have like one part of the laser beam will be slightly out of phase with the other part of the laser beam, because you're going to have a variety of photons that are contributing to the beam of light, and those photons are going to have a variety of wavelengths. Even though it might be constricted in wavelength space, it's not zero in wavelength space. And so what do you do about that if you want a coherent laser light? Is you have to hook it into a system of mirrors, for example, in order to remove wavelengths that don't fit. You put it into a cavity so that only specific wavelengths will fit inside that cavity, and it will remove all these wavelengths. They won't fit in the cavity, so they'll bounce off of the mirror. And then you have it in the cavity, and then the light that comes out the other end will be a more narrow wavelength and have a longer coherence length. So these are all different ways of messing around with the wavelength and frequency of a laser. When you're talking about the position and momentum of something, you can describe the position of a wave or the momentum of a wave. You can describe a wave either through the position representation or through the momentum representation. Okay, it's similar to saying I can define a curve as a series of points, or I can define a curve as a series of velocities like tangents. Okay, so I'm trying to do this. So here's a series of tangents to a curve, and I can get the same curve out of it. So this would be like a representation in momentum space, and this would be a representation in position space. Okay, so that is that's what's going on with the Heisenberg uncertainty principle. So you can represent something in position and momentum space. However, you can't know both simultaneously. So you have this phase space available to you. You have an object can have a position and it can have a momentum, but these two things are limited. You can only constrain the particle to live within a box with an area of h bar, of Planck's constant. If you try to, so this is like its momentum. You measure a particle's momentum. This is your uncertainty. You measure a particle's position. This is your uncertainty. If you try to improve the precision of the position measurement, what will happen is as you improve the position measurement, the momentum will squeeze out. So as you improve the position measurement, you have to preserve this area. Okay, physics does not allow you to constrain it to an area smaller than that. So the area is still h bar. Now the position is more tightly constrained, so you have a better position measurement, but now the momentum is completely haywire. You don't know what the momentum state is. Your uncertainty in momentum has increased. By the same token, if you want to constrain the momentum, then the position is going to stretch out. So if you want to have a good constraint on momentum, like this, so now your momentum measurement is small, the position measurement gets larger. Again, the area here is going to be h bar. And so these, there's basically, electrons have their own private space. You can't get smaller than that. And so they will mush around in phase space, the phase space volume where you can isolate them. So you isolate them with your measurement. You make a measurement of position and momentum. As you make that measurement, you're trying to constrain the momentum to live inside some box, and there's a minimum box that it can fit in. And so as you improve one of them, then you destroy your knowledge in the other one. In typical cases, this is not an actual class. This is me just going off on this stuff. So in typical cases, your uncertainty and position and momentum are really big. And so like your error bars are going to be a huge thing that doesn't place any constraints on it. But you can arrive in situations where, with high precision measurements, where you can do this. So let me give you an example of what it means to have something. If you constrain the momentum to be very precise, so here's your precise momentum measurement, then that's going to correspond to a wavelength, a specific wavelength. Okay, and it's a plane wave that extends forever in along there. And that's why there's no position anymore. right? It doesn't mean anything to have a position. What's the position of a wave, right? Here's a wave in the ocean, or here's a train of waves in the ocean. What's the position? Well, the position, it's everywhere. The position is everywhere. If I zoom out, then here's that wave. What is the position of the wave? This is a definite momentum space. And as a consequence, because it's a definite momentum space, it's an indefinite position space. If I were to shorten this wave, then I can get, here's my shortened wavelength, and the momentum space will also be shortened. So now I've got a momentum measurement that is constrained to some range of values, and I've got a position measurement that's constrained to, this range of values. If I, on the other hand, constrain the position of a wave, so now my position wave function looks like this. So this is position. It's like basically a delta function. Then what do I get? If I look at this in momentum space, so if I do the Fourier transform of this into momentum space, then I'm going to get a single momentum state. So this is my single momentum state. Okay, and that extends, I get a wave, I get an ensemble of momentum states. So if you want to produce this kind of delta function in position, you need to have all frequencies. Let me draw this again. I didn't do a very good job. If you want to constrain the position of something, then all frequencies have to contribute to constraining that, because one frequency is going to contribute here, another frequency is going to contribute like this, another frequency is going to contribute like that, and these all have to sum together to produce a position like this. And so all frequencies are have to contribute in some way to produce this. And because all frequencies contribute, there's no longer a frequency. There's no longer a momentum. Remember that momentum is energy over the speed of light, which is hf over the speed of light. So this frequency right here. So if you constrain the position, then all frequencies have to contribute, which means that all momenta have to contribute. And so you can no longer say, here's the momentum of this object, or here's the range of momentums of the object, because the range is infinite. So that is when you can localize the position, so this is when you localize the position, the particle's wave function to a particular position, then all momentum states have to contribute in order to force it into that position, and vice versa. Now, what you can do in some of these cases, and this is what happens at LIGO, for example. So at LIGO, they have a way of operating where they force noise. So LIGO is an interferometer. It comes in, you have a beam splitter, you have light that goes in these two directions, it comes back out on this side. So there's a mirror here, there's some cavities in there. The light comes back out, and what they'll do is they'll measure the properties of the light coming out, and they will inject noise. They will deliberately inject noise into the tailpipe of the interferometer in order to produce a squeezed state. What the squeezed state does is it basically adds noise in momentum space, the momentum representation of the light that's coming out. It adds noise in the momentum space, which reduces the noise in the position space, and therefore allows them to make higher precision position measurements of the elements of their interferometer. So they go into this squeeze state mode. It's not effective at all frequencies, but you can tune the frequency you want to be effective at. You inject noise at a certain, you inject momentum noise basically into the detector from the back end. So you have to characterize that noise first, and then you can respond to it. And that constrains the position of the mirrors. And when you constrain the position of the mirrors, you get better precision measurements of gravitational waves that might be messing around with the positions of the mirrors. So that is the, if we look at the squeeze state, LIGO squeezed state. So I open this image right here so we can see this LIGO image. So this is the LIGO sensitivity curve. Typical noise without squeezing is red. So here's the noise without squeezing. And the shot noise is this line here, so that's noise that you get from quantum mechanics. The fact that photons are individual bunches, which means that you can have an average power, but that average power is going to be made up of particles arriving at random times, so that's called the shot noise. And then you can see the squeezing enhanced sensitivity that in this case at longer wavelengths, at higher frequencies, this is frequency space, at higher frequencies, they get improved sensitivity. So for this range of frequency, they get improved sensitivity, and you get worse sensitivity at other frequencies. So you can see that it's peaking up above the red line here. So that's when you have squeeze states, you can shift the wavelength where you're sensitive, this is probably with a scan. They're probably scanning through different frequencies to get it to line up. Because I think what happens is you actually get kind of a dip, like there's a specific frequency where you're more sensitive, and so you just tune that dip and ultimately can build this structure. I could be wrong about that. I don't see the image that I was expecting to see when I pulled it up, although that is supposed to be what shows it. Is it showing up here? Here, this is more like what I was looking at, or more what I was thinking. Okay, so here is the thing. Here's the squeezed light that's coming in through the signal recycling mirror back into the interferometer, and then you can see advanced LIGO. Here's the advanced LIGO sensitivity. This sloshing SR. That's probably I think that's the squeeze state. So that's where it comes in. Here's the improved sensitivity right there, that bump. And then as you change like what signal you're putting in, what noise you're adding to the system, then you can move this increased sensitivity, like that band where your sensitivity goes up, you can shift it to the right or to the left. Okay, there we go. That's quantum mechanics. That's that chapter in quantum mechanics. Okay, does anybody have any questions? I'm happy to answer questions. There was a question earlier that I missed. The question was, what about particles splitting into other particles and then reforming before hitting the destination? So all along the way, when these particles are going through, their life, they interact with the quantum fields around them. So you can have, alrighty then. Well, I guess I'll just talk about it. So as the particle's moving along, you're going to have, like an electron is going to interact with the electromagnetic field, and so it's going to have photons that are coming off. The photon's going to create virtual particles. I really need my drawing pad to do this. This mouse pointer is messing me up. Let me try messing around with the mouse pointer. Maybe I can get it to my drawing device to come back up. Okay, hold on one second. Accessibility. Display. Small mouse pointer. We'll see if it works. No, it doesn't. All right, let me pull this up a new one. All right, we're just gonna start over. Okay, hold on, I gotta pull up a new drawing pad so I can draw this amazing picture, because it's gonna be an amazing picture and everyone's gonna like it. Okay, but as this particle is moving along, it's gonna interact with whatever fields are in the area, and there's gonna be a sea of virtual particles that form around it. So it can split, it can pair produce or whatever as it goes along, but the probability of each of those interactions happening is gonna be less and less and less, the more complex the interaction is gonna be. So you can have, here's your electron moving along. Electrons are straight. Here's an electron moving along. It can interact with the electromagnetic field. That electromagnetic field can pair produce another electron-positron pair, come back together. And this is a diagram, or this is an interaction that you account for when you calculate the action. So you have the action for this path. That action is going to include all possible deviations from that path. Well, deviations, like all possible interactions with the fields that it couples to along the way. So it could come along here, it could interact with the cosmic neutrino background, and that will affect how the action, like how you calculate the action in the end. So that is something. So that is particles splitting into other particles and reforming and hitting and stuff like that. That's something that can happen. I was wondering about the meaning of that. Uncertainty says it doesn't have a position, we can't measure it, or really doesn't have a position. Is there a difference? So the uncertainty principle says that the wave function is localized. Like you have some wave function, it's got some so the electron has some probability of being at any point in space. The probability can go very close to zero, and it can go very close to zero very quickly, but you can localize it. As you localize the position wave function, then it expands the momentum wave function, simply because when you do the Fourier series, if you're trying to build you're trying to build a standing wave, you're trying to build a shape. If you're trying to build a shape out of a bunch of waves of different wavelengths, then the more narrow the shape is, the more frequencies you have to add to contribute in order to get this feature. So if you do, when you're in like a signal processing class, you might have a square wave or a sawtooth wave. And if you want to build up a sawtooth wave, then you have to, if you have an abrupt feature, like if you built up a square wave like this, so you have a signal generator that makes a square wave. As you build it up from different lower frequency sine waves or a series of sine waves, then you're going to get something that goes like this, and it jumps up from the Gibbs phenomenon. It overshoots. So this is a series of contributing frequencies, and the sharper the feature, the more high frequencies you have to add, and the more high frequencies you have to add, you're basically expanding it out into the continuum, into all possible frequencies. Okay, let's see. If you measure where it will be by a formula, then you can't know its position. Well, you measure the probability of it. So the wave function tells you the probability of a particle having a particular property, whether it's a particular position or a particular momentum. So what you calculate the evolution of the wave function, and the wave function tells you the probabilities of the particle being in different locations or with different momenta. If you know the position, then wouldn't the momentum be zero because it would have be at a particular spot? But the momentum tells you its future trajectory, right? So the position tells you its instantaneous location. The momentum tells you its future locations. And so if you measure the position of something very precisely, what you're basically doing, so the traditional way of deriving this is to say, here's this object, I'm going to hit it with if I want to measure its position, I have to hit it with a wavelength of light, where the wavelength of light is comparable to the amount of localization that I want. So if I want to measure its position to within this, a box, an uncertainty of some amount, then I have to hit it with light with a wavelength less than that amount, less than or equal to that amount. Well, that means that light is going to have some amount of momentum and some amount of energy. And the momentum or energy of this light, the more I try to localize that light, like the shorter the wavelength I have, the more precisely I can measure the position, but the more momentum and energy I'm imparting onto the particle itself that it can recoil from. So the photon comes in, bounces off of that thing, bounces in a different direction. This is where I can look at it. So here's me standing here looking at this photon. So now I've localized the particle at that instant to be at a given location with very short wavelength light, so my uncertainty in the position is very small, but the momentum or the scattering that I get from that, the back reaction of the particle, is very large because I hit it with a higher energy photon. So that's the traditional way of deriving the uncertainty principle. A different representation or a different way of doing that is to say that all momenta have to contribute to produce a spike in position like this, and therefore all momenta are available, which means that the particle is going to have momentum. It's going to have a contribution. Its total momentum is a contribution of all possible momenta, which means that you don't know what its future trajectory looks like. That once you localize its position, it can be moving, right? A car moving down the street, I can identify where the car is located as it's moving down the street. I can identify its position directly, but that doesn't change its motion. So when one says, I want to measure the position of something, they're talking about, I want to measure the position of something at some instant in time. Hope this was worth your while. I'll be back on Thursday. Thursday, I have a guest. Thursday, I have Thursday's going to be a big stream fest.